Okay, my friends, I'm just going to start this off by saying we found these particles, and here they are right here in our experiments. Those are the particles from Fermilab. These are the same particles. Now that's from light, and this is a photon photographed using CMOS. What happened was we accelerated that light, and you can see it accelerating right here. Normally that wave would be a nice, clean, roundish wave and just continue going like that. But we accelerated because of the Venturi. When we did that, we were able to separate the black from the white. So we actually divided these two particles, and these are the smallest particles that exist, and they know this at Fermilab and CERN, Lawrence Livermore, all these places. They've seen them, but all they do is see them in a pile of debris. We see them as they are emitted as light, so we understand this is a dipole. That's a dipole. Back to back, they make the most tiniest stable particle, which is a photon. Below this is just one of these, and that's an electron, a black and a white. Nobody's ever known about the black. The black is dark matter. It's never been understood. Let's go and look and see what they have to say in physics. Okay, my friends, today we're going to go over the speed of light, which is not a constant. It has been always represented as a constant, as a law. So they have had to fit physics into the speed of light, and the speed of light is not constant. Now Astrom just did a very nice video about this and saying yes, the speed of light is not correct. They say it can be reversed, going backwards in time. Now I don't know about that, but I can tell you right now the speed of light is not constant, and because of that, modern physics being based on that principle, virtually nothing in subatomic physics in the quantum realm is correct, because quantum is where light is, way down into the tiniest particles, and it's virtually light is only two of the tiniest particles that exist, and it ends up being dipole electron flood theory. States that everything there is made up of dipoles. In other words, instead of one big proton, as they claim now, is what they're trying to smash to bits to figure out what's inside of that proton. What is in that proton? Well, I can tell you what's in that proton. There's 1,823 or so tiny little particles that are dipole electrons. That's what my theory is based around, dipole electron flood. Everything is flooded with these particles, and they condense and congeal at certain intervals called periods on a periodic table. In other words, hydrogen is not one giant proton and one tiny little electron. It's 1,825 or so of these dipoles. So the periodic chart has to change, physics has to change, a lot of things have to change because it never worked in the first place. So let's get past this speed of light, and I've shown it hundreds of times, literally, probably 1,000, that light can exceed its standard speed and increase in speed, and it can slow down, and that is just in the air. Now in space, it's saturated with particles as well. There is no vacuum in space. This is not something that is unknown. And for a particle to pass through these fields, it is being suppressed, it's being resisted. It's going boom, 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 boom. And by the last boom, it is the cosmic microwave radiation, which is nothing more than light particles just barely drifting around out there because they've lost their forward momentum because they banged into enough fields, which is called the quantum foam. Blinking on and off, that particle goes blink, 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 and then it just stops. That's what the whole thing is. The universe isn't expanding exponentially anymore. It might be expanding, I have no idea, but I can tell you what, that's not why the light is being pulled away from us. I don't believe that redshift is correct at all. It's just not right. And we can't tell where things are in space because the light coming to us is slowing down, and it could slow down more from here and less from over there. So we have no, it's not homogeneous. So let's get started. Okay, this is Fermilab again. They say empty space isn't empty, is saturated with these subatomic particles. And what happens is there's a dizzying display of change out there. Empty space experiences similar activity as the head of a root beer, with subatomic particles winking in and out of existence. The subatomic particles are real and have a measurable impact on our universe, absolutely. So as these light particles come through, they go bang, 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 and they blink on and blink off, blink on and blink off as they're hitting. But every time they hit, they lose speed. They come slower and slower. Eventually they become just sort of laying around out there. Cosmic microwave background. Alright, this is a great place, Astrum, very good channel. And they're talking about light being just totally wrong from what they had always thought. And they say light can even go backwards through time, and this experiment proves it. Well, I can show light going backward as well. Okay, so we're talking about going faster, we're talking about going slower, we're talking about reversing light. And they go into some kind of sort of exotic explanation. Let me show you my explanation of light speeding up and light slowing down. I can actually show you rather than the actual little diagrams. All right, so let's start out with what light is. This is a pulsed red laser. Each one of these is a pulse of light. Inside of the wave is a particle. And that particle has a magnetic field around it. That's why you see this wave. All of the other particles in the air, all the gases and so forth, are made of the same materials as light. They have little magnetic fields in them. And if they are pushed against, they will glow a little bit. And that's how heat gets infused into things. These will get a little bit warmed up as this passes through them. It's just the way it works. Field against field creates a heat. Now, these are the tiniest little particles, and let's look at what the particle is here, and as it moves forward, how it creates this effect. Okay, this is probably the easiest way to show it. As I showed you, Fermilab has seen these particles. That's a fixed particle. That's a puffy one, and you can see how it can get puffy and smaller. That's this one. And the black one just never changes. I agree. And it has a fuzzy edge around it, just like they show. I agree with that. This one has no mass. I agree with that. But together, two sets of these make up a photon. One set is an electron. That is electricity, but this is the electric part. This is the carrier part, and it carries the white. All right, so, and that's what an electron is made of. This is basically the smallest particle there is. Now, and it is a dipole, which means it has a positive end and a negative end. A dipole means two poles, positive and negative. Now, we put it through a Venturi, and that's really the only reason you can see this. And you see the particles ahead of it are getting excited. Let me turn this down so sometimes you get a better shot of the picture. Now, this is, again, these the same particles that Fermilab and CERN and everybody's seen. And they can, one gets glowy and one gets small as it moves through the air. As this charges up, because it's banging into other particles, it gets charged up and it will flip to the back, and this one will flick to the front. And that's what creates the spin, basically. Up spin and down spin. Now, this is what happens when this particle is accelerated through a Venturi. And bam, through the Venturi, and it literally separates the black from the white. Remember, they're attached. All right, this is just a black and white of this one. So this gives it actually colors of the intensities, and the center grows real glowy, and around the edge they're a little less glowy. And then when they pump up, they flip to the back, because this will get almost nothing, and then they'll flip to the back. And it's the same ones, the green, the red, the green and the blue and the red, they're all the same particle. And I can show you the green one. The red one, the blue one's very hard to see. Now, when this came through the Venturi, you can see it's accelerating like crazy. I mean, that is just acceleration on steroids. It's like a rocket ship pulling out of its own wave. And then here it hits and the black separates from the white. All right. This white is nothing more than raw electricity. This is what does all the work, and we can separate it just by putting it through the Venturi. We did no more work whatsoever. In a generator, you have to work like hell to pull that black away from the white and push the white into a battery. We can squirt it right into a battery. I mean, it's amazing, to be honest with you. Okay, just look at what you have here. This wave is accelerating, and it's because of the magnetic field is being pulled forward. That's where the particle is, that little tiny particle I showed you. And as it stacks up against itself, it's being pushed back, so it gets brighter and brighter and brighter, and it explodes at the Venturi. You see these reverse electromagnetic force? That's because of this explosion. Now, is that light traveling backwards? I don't think so. It's just light being re-emitted from the explosion. And this is literally a subatomic nuclear explosion. The nuclear bits are breaking apart and forcing the expansion of this wave backwards, just like an atomic bomb. And I will show you an atomic bomb doing precisely the same thing. And for the first time in history, we have captured Whistler waves. Something you've never heard of, I'm certain. Remember this Venturi is only letting the white through. There is not one tiny taste of black here. It will come back to reattach to the white, but only because the white is slowing down enough for the black to reattach. Here, there is not one bit of black. Now, another Venturi setup did this. This was when some black came through with some white. Now you see what you're seeing here? Remember I talked about Whistler waves? Whistler waves is in the very low frequency audible waves. These are Whistler waves. And they are produced because of this white bouncing against the other electrons that are in front of it. Bounce, 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 bounce. And they're slower than the waves that are coming out. You see how fast these are? These are slow. These are what's called Whistler waves. And these will make a sound. So when an atomic bomb goes off, what you hear is and then nothing. And, you know, it's very, very bright, and you hear and that's it. And then a little, because that's these. They are radiated out at very, very fast. Now the black one takes a long time to get to where you heard this. So you're out here. The bomb goes off. You can see a huge, brilliant glow. And you hear almost instantaneously. And then about who knows how long after, it depends on how far away you are, the black and the white come together and that's when you hear the bomb blast. And I have evidence to support that and the fact that this has no mass, the white. It just burns stuff up and they just dust off like vapor. And here it comes. Here's my proof. Before I go to the proof, don't forget, I'm claiming this is a subatomic nuclear explosion. And you will see a nuclear explosion do virtually exactly what this would do. The white hits and will burn whatever is up there, and the black hits just after. And when the bomb goes off, you hear the Whistler wave first, which is the audible part. And that's a little later, boom, everything goes. All right, this is atomcentral.com. What they have here is a test house. All right, here it goes. This is running very slow. Now, that's the test house. I'm going to stop it here. And what they're going to do is see what happens when a nuclear bomb hits it. They have a hardened enclosure with a camera facing this direction, which is not going to get impacted by the nuclear blast. It's a very, very hardened structure, and it's got the facing away from the incoming radiation. Now, when it goes off, here's what you're going to see. It's just you're going to see a huge glow of everything. All of the wires, the poles, the roof, the whole facing here, it just all vaporizes. Now this is not facing directly, so it's not going to get hit and vaporized. This is not going to get vaporized because it's not combustible. Anything that's combustible, zip, it just turns into vapor. Watch. And I'll stop it here and there. So now the first thing you're going to see is just the glow, like unbelievable. Every single, I just stopped it. This is just the first part of a nuclear bomb. Now watch all the poles, watch everything, because the electrons, which have no mass, are hitting this thing. See, they just burn up. Look, nothing. Nobody's even moving. It's just, look at the poles. Look at all the wires. It's just an infusion of extra electrons, and anything combustible. And you got to think about this carefully, because there's a lot to learn here. Anything combustible. What does combustible mean? What does combustible mean? Why does this vaporize like this? We got to think about combustibility and what combusts and why we get these vapors and what is involved in these vapors. That's a whole other issue. That's in the chemistry end of things. But let's talk about the physics part of it. Nothing has moved. Nothing has moved. That's an atomic bomb just went off, and it's just smoking. It's just smoking up everything. Not a single thing has moved. Now comes the black. Boom. All right, you see that? That's the black particles. The black and the white are hooked together, but the white, it encrusts. The white encrusts the black. So when it goes off, the white goes first. The black comes behind it, pushing it, just as I showed you in our light experiments. All right, so what I just showed you is the atomic bomb going off, nothing but whiteness. And then where the house is, we see the house smoking up, and then the black hits it and knocks the house over. Well, what's this about this Whistler wave I was talking about? What is that? You see how many lines there are here? This is in extreme vibrations. These are much less, you see them? These are in the audible range. There's the high up in audible range, but you'll hear them. And I can show you this. As an atomic bomb goes off in the desert, people are sitting way out here, and the first thing they see is pew, and then they hear brrr, and then a little while later, boom, they get the blast, hits them. Here it goes. And you can see the wave going across, the black wave going across, disturbing the sands. But already they've heard the Whistler wave. All right, this is from a video I did a while back about these Whistler waves. Now, you're going to see an atomic bomb blast go off. The sound may not sound too good because it's we're listening to the sound from the old video, but let's hear it. Here's what happens. You're going to see the bomb blast go off, and then you're going to hear brrr, and that's the Whistler wave. And then shortly after, you're going to see it'll hit the impact. Here goes. Boom. Did you hear that? You must have heard that. Brrr. Let's do it again, because that's the Whistler wave. It's instantaneous almost. Here goes. You see, instantaneous. Instantaneous. You didn't see any nuclear blast yet. You can see it. But now it's coming at us. You see this? This is the dark particles coming at us. That's the bomb wave coming across the desert. So we have not heard anything other than that. Now we're going to hear the blast. Here it comes. It's coming. It's coming. There it is. That's the blast. All right. Okay, so you're sitting way out here. The bomb goes off. You see a flash, and you hear. Brrr, that's these. Now this keeps moving and moving and moving and moving and moving and moving and moving. And all of a sudden, bam! You get hit. That's all it is. That's the Whistler waves. And that is the black particle that pushed down the house. This is the white particles that just made the house burn up. Okay, so like I say, Astrum, very good channel, but they got a lot of things in here I would like to discuss with them. I have different interpretations, and I believe I have the evidence to support the things that I say. Like this, and the Whistler waves and the speed of light can slow down. It can absolutely slow down. That's the blue coming in and then slowing down. You can't even see that there's two particles. There's the two little dipoles until it gets way out here and slowed down, and then you can see them. Blue is just very, very, very fast. The red is very slow compared to the rest of them. Here's the red coming across. Let me turn this off so you can see these better. I'm going to just run through these and we'll wrap it up. These are the neutrino phases of the photons just before they exploded. These are neutrinos too. They're not fully photons yet. Then they explode over here. Now, the green is exactly the same. You see the green coming through? Exact same particle, no difference whatsoever, only it's much more powerful. And here is the, I don't have it here. I have green and red coming at the same time. Hold on a second. All right, see here? Here's the red coming through, just pushed out of the way. The green is just powerful as it can be. And it reconcusses out here. It's just pushed the red out of the way. So that's the difference between the energy values. And they spin, they're not flappy waves. They're spinning in a circle like this. And that makes this spin into a circle sideways. They don't ever do this. That's just totally unusual to be spinning like a barrel roll. They spin like this. That's the way they spin coming through. They don't barrel roll like that. That's because this field is so powerful that just pushed it in their fields and spun them this way. That's just not normal. Doesn't work that way. All right, this just shows you the interaction between the light particles. They do not want to be grouped together tightly. They sort of push each other apart. These are just too tight, so they get really glowing. As they get apart further and further, they get less and less energy, so they don't glow. The energy is push to shove, magnetic field against magnetic field. These are all these spinning little particles, and light does spin. Of that, there is no question. This is light spinning. This is a slit. This isn't a big round venturi. This is a slit, straight up and down. But it is a venturi because it forces the particles to come in to a focus point. And when they do, they screw through here, just like this. They come through just like this. There's a little tiny particle, which is the photon. It spins, sometimes it goes that way, sometimes it goes this way. There's thousands and thousands of them going at the same time. They're just everywhere. So most of them go through the center, and when they do, they hate each other, so it gets real glowy. That's not what you see in an average double slit experiment, because they got one going over here and one going over here, and they sort of bang together in the middle, but not enough to do this. This is, all of them have to go through that one slit right there. And then, of course, on the other side, they could create that repulsion pattern. The whites do not want to be next to each other. They hate each other. So they push each other apart, and they create these stripes going down, which they call interference patterns. They're not overlapping flaps because it's a double slit. This is a single slit. So that's wrong. All right, here's what CERN, Fermilab, and all the colliders do. They use big protons, but a proton, they don't realize, consists of nothing but little dipoles. So they're taking two huge things, smashing them together, and then they're getting all this debris. Every now and then they get the correct particles. They'll see the littlest, bittiest ones, yes, but they don't know where they came from. Because then they'll see a chunk like this, they call it an X chunk. It's just a big blob. And then you see some have a couple of particles together, and some have 5 and 10 and 50 and 100. And they call it the particle zoo. Because it's just a whole zoo of particles. And here's what it looks like when they make that crash. This is their Higgs bosons. These are Higgs. These round circular fields. But they're taking a batch of these together, and they're coming back, they're going around, 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 and boom. And when they hit, they just make all the debris. And then they dig through it. They found the particles, absolutely. They found the same particles we found. And here they are right there. These are the tiniest particles they can find, and they're what light is made of. And light is made of two dipoles. And we split the dipoles, which it really is fission, and that's fusion. It's the only way you can look at it. And in between, you have raw energy. This is what we need to run our cars and batteries and everything we have. And we didn't do anything whatsoever to separate the black from the white, other than put it through the Venturi. And this could be done, thousands of these, in a little lunchbox you could carry around and have probably as much power as you could ever use. Because that's all you want to do, is put that white into into your car or whatever you have that you want to run with electricity. Electricity has no weight, which I showed you. That's the white that burnt the house down, and it's just burnt it. There's no weight there. It's zero. And the same thing when you charge up your car, it doesn't get heavier. It doesn't get heavier at all. You run 500 miles, you go back, you charge it all up, and it's now all big, powerful again. Didn't change the weight. All you did was put in these white particles. Now, there's no reason whatsoever that I can think of, and I'm seeing them going crazy trying to figure out how we're going to get energy, and here it is right here. You take these lasers, you shoot them through that venturi, and on the other side you put a solar collector. Basically, that's it. And it just goes and shoots it right down into your battery, or right into your car, whatever you want. And you could carry them around. They're portable. You're never going to get hurt with this because you're only using light. The reason you get hurt with atomic bombs and so forth is because instead of one particle coming out, which is just light, you're getting hit with what's like that, or like this. Gigantic chunks that tear you to shreds, that tear your DNA to pieces. One little light, you're getting this all the time. All day long, you're getting the same stuff as what we're here. If you put your eyeball right there, you're probably not going to do too well. But if you, this is instantaneous. They're back to being reattached. Instantaneous. So this cannot hurt you. It's not dangerous. It's all that you're doing is separating the white from the black, and then the white does its job. And you can do this all day long, shoot this through. You never even have to stop turning the laser off. Okay, you don't have to be any kind of a geek to understand this. It's very simple. I'm going to read you this, and then I'm going to explain what it means. It says there's alpha decay is one type of decay, and it's a radioactive decay in which the atomic nucleus, which is the nucleus, is the core, emits an alpha particle, and thereby transforms or decays into a different atomic nucleus. So the alpha particle is the big chunks. All right, so it emits a whole bunch of stuff and turns into something else. All right, so that's how the decay happens. Instead of being one big thing that's unstable, a chunk of it goes flying off and it becomes two different types of elements. All right, now that's alpha decay. That's the big chunks. Now let's look at beta decay, because that's what we do. All right, now this is ultra simple. This is beta decay, electron emission. That's what I deal with, is electrons, because we started with light. We didn't start up here. We started down here. So we're only working with electrons. So we are only working with beta decay. Remember that. Very important to understand that principle. All right, remember this. This is what they're using, is big protons, which consists of 1,823 black and white particles, red, green, blue, whatever, but the black is always the same. And I believe they crust over, the black goes to the center. We never can see the black, because anytime we look at it, these bounce back at us. But inside of that crust, like an eggshell, is the black, I believe. Now, I had originally thought it might be this way. Each black and white was together all the way out until you hit the red, which was just barely being held. But the blue down here was real tight. Now, I think it's basically this, but only the black congeals to the center. One way or the other, it doesn't matter. But it's 1,823 particles. Now, what happens with a neutron, which is 1,824? A neutron can give up one of these particles and become 1,823 and become an electron, and guess what? That's exactly what they say it does. You see, this is what drives me crazy. An unstable atomic nucleus. What makes it unstable? Why is it unstable? It has an excess of neutrons. Who says that? It may undergo this one electron decay. This is electron transmission. One electron goes flying off. All right, so you have a neutron, 1824. One of the electrons goes flying off. All right, then the neutron is converted into a proton, which is 1823. It's exactly what they say. An electron and an electron antineutrino, this is the particle that goes flying off, the antiparticle of the neutrino. So it's identical to what I have been saying for years. That's the electron flood theory. The core is made up of all of these excess particles, all of these particles that are 1823 for the proton and 1824 for a neutron. And it says the neutrons may undergo one, which is a beta decay, one particle going, and the neutron is converted into a proton. Exactly. And the electron is this little particle that went flying off, and they call it an electron antineutrino, or the antiparticle of the neutrino. Well, there's the electron, the black and white part, which I showed you very clearly. Very clearly. All right, so let's say there's 1824 here, and then one of these goes flying off. It becomes a proton. So 1823 is a proton, which is out of balance. All right, it's charged. It's got a charge on it. It either wants to give one up or take one on to become neutral, just like a neutron. So the neutron gives one up, it becomes a proton, and it ends up with 1823. It's not very complicated at all. And how could the proton just be unstable and give up one here or there? And there's a million zillion little particles in between every proton, and they're called them isotopes. An isotope means that, like, instead of carbon being just carbon, one carbon, and that's it, there's a zillion different carbons. Let me show you how many isotopes of carbons there is, and they don't even know how many there is, because all they're being able to look at is the ones that they can see, the half-lives. The other ones are there, but they never can see those half-lives. Let me just show you carbon. Okay, look at this. This is just the isotopes of carbon. Carbon is not just one carbon. There's a zillion of them. All right, now, these are just the isotopes. Now here, it's very easy to understand this if you just pay attention. There's carbon 12 and 13, they say are pretty stable. All right, so they don't want to give any up and they don't want to take any on. But you go below that and they want to take some on. So you're down here at, this is how much they weigh, 8, 9, 10, 11. All right, and then you go up to 12 exactly, becomes stable. And then 13, pretty stable. And then you go up over the top of stability. You got 14, 15, 16, 17, and they just keep going up. 18, 19, 20, 21, 22. Well, what is that? Those are just more and more particles. And they don't know how many there are because there's a bazillion of them. These are just the ones that they can measure the half-life. And these are the decay modes. They're all beta decays. See it? Beta, 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 beta. And that's given off one of these little bitty particles. So they're all over the place here. And all it is another ball of little particles. It's nothing to do with a big proton like that and a couple of little quarks. And they smash them, they go every little bits. They're smashing these. And they're just getting chunks of this and chunks of that and chunks of that. It's a particle zoo, they call it. And they are correct. It is a zoo. Okay, so I'm going to leave it at this. This is the new atomic model. This is electron flood theory. I showed you the particles, and the only two particles that exist is the W and the Z boson. The two of them together make up that diarac, the red and the black. Or green and black, blue and black, whatever. But the black is the Z boson. That's where all the weight is. The W has no weight whatsoever. It can get big and get small, just as I showed you. The two of these together make up a gluon, which is literally an electron, but it has that black side to it nobody's ever known about. Two gluons, which are these two back to back, two of them, make up a photon. End of discussion. Higgs appears only when the W and Z are split, the black and the white, and they come back together. That's when they create that spinning Higgs. The Higgs doesn't create these particles. These two particles create the Higgs. That's another thing they have wrong. All the rest of this stuff is just what they call the zoo, that is these in different configurations. A few extra ones, a few less ones, spinning up, spinning down. They call them strange, top, charm, quark. You know, all these muons and muon neutrinos, and the neutrinos are just different phases of energy of the same particles. That's why they say they keep changing flavors. Well, they're stacking up on themselves. And as they stack up, they get more and more and more energy, or less and less and less, whichever way you want to look at it. And, you know, depends on what it's going into. And at that point, they become a different particle. They will say, how could it change? Well, it's just changing mass, because the mass is the impact value, basically. And as they stack up on themselves, they gain energy because they're being pushed against the other fields. It's field to field. And every time you create a field to field interaction, you get that glow of energy. All right, I did show you that we created electron showers. Of that, there is no question. We didn't have to do proton-proton decay, all this nonsense. We went right from the energy of the neutrinos, and we can splash those neutrino white particles only. Those are the electron neutrinos, and they create electron showers. That's what this is all about, electron showers, the physics of it. And they can create from a few 100 billion electron volts to trillions. As I showed you, we're just squirting that white, and that's all you want, is those energy of the neutrinos. And that's what we're producing in that stream of energy right there. This is literally a subatomic nuclear explosion. That's all it is. The particles are separating. This is fission. Back together here is fusion. In the middle, we have just nothing but raw energy, the stuff that burnt up that house, and the stuff that drives cars. It doesn't weigh anything, but it does a hell of a lot of work. You see that? These are Higgs fields. And these Higgs fields are created when the white separated electron showers reattach to the muons. So the muons are just laying around everywhere, it appears, because they didn't come over the top and jump ahead of this. When we separated them at the Venturi, right here, the black can't get through. It hits and bounces back. It keeps banging and banging and banging, pushing the white through. Well, all the blacks show up all over here, and they start accumulating from every spot. They reattach to the white. Okay, so I'm going to leave it at that. That's my case for a new physics. And the new physics atomic model is dipole electron flood theory. And I believe I have shown that it's viable. And the black is gravity. This was done in outer space in the Russian space station, and they put in charged particles into a vacuum chamber, and this is what happened. All the black went to the center and all the white ones crusted around it. That's virtually the same thing that's happening to Earth. Earth has to be saturated with dark matter, because all electricity bzzz, goes right to ground. Static, boom, right to ground. Lightning, boom, right to ground. Electricity, bzzz, the Earth will suck in all the white particles that you can present to it. So we literally, if you could think of it, we are a black hole crusted with all the particles that make up matter. And they glow and bounce back at us. These glow and bounce back. This doesn't emit, it doesn't absorb, it doesn't reflect. It's literally the dark matter they've been looking for. It's attached to the light. They never realized electrons, this is an electron, but it's got the dark matter attached to it. Nobody ever realized that before. They always thought it was just a glowy thing, was the electron. No. And this is an electron, another electron. Back to back, they make a photon. You take 1,823 of these, and it makes what's considered a proton. And they seem to be stable at certain quantities that they call them the periods in the periodic table. So you got, and trust me, there's hundreds of thousands of particles when you get up into these heavy ones. There's not just 90 or whatever. Every single particle that they claim is a proton or a neutron consists of 1,823 if it's a proton, because it's charged, it's not even. 1824 is a neutron. It doesn't want to take one more in or give one up. It's happy because it's neutral, because it's even numbered. Once you go odd numbered, it either wants to give one up or take one on. That's what protons are, and that's why particles will create molecules, because they have excess charges that want to give some up or want to take some on. That's what a molecule is designed from is these charge separations that want to work with each other. All right? I love you all. That's physics for today, my good friends. And I would love to be able to talk to somebody in the Department of Energy, which I've been trying to get through. I can't get through to anybody. I would like to have them take a look at this. It'll only take a couple of weeks to tell one way or the other. Will it work or won't it work? And I say it will work. And I will be glad to confer with anybody that is willing to discuss this on a level that can make something happen. I can't make anything happen. I don't have the resources. And I can't get through to anybody to even discuss this. So, I love you all. Hope for the best. And we need this energy. We need energy desperately. And they're doing everything they can. They're thinking of anything. And the Earth is being destroyed while they're just missing the boat. As far as I'm concerned, dipole electron flood theory has got every chance of getting us out of this disaster that we are currently in.